This webinar has been put together for the Imperial Barrel Award Committee in conjunction with the American Association of Petroleum Geologists and the Division of Professional Affairs in order to help you improve your interpretation and, just as importantly, your presentation of your project to the IBA judges. The techniques and methods discussed in this presentation will not only help you with your competition, but in your career as well. So this webinar is entitled Evaluating and Presenting Prospects. The various methods and techniques that we present in this webinar come from a number of various classes taught for subsurface consultants and associates. My name is Bob Shoup. I'm a board-certified petroleum geologist with over 40 years of industry experience. In the course of my career, I have discovered over 135 million barrels equivalent, and I have an exploration success rate of over 46%. I'm an instructor for a number of courses, including classic depositional environments, petroleum systems evaluation, reserve estimation, basin play and prospect evaluation, and structural mapping. When presenting a prospect to management or to the IBA judges, you have to do two things. First, you have to demonstrate to them that you have interpreted and mapped the prospect accurately and properly defined the risk and the uncertainty that go into determining the prospect's potential. And you must present that information to management, or in this case, the judges, in a manner that allows them to quickly understand the opportunity and how that opportunity rates against other opportunities that they may have to consider. The outline that we will follow in this presentation is to show you how to first set the stage, then to look at evaluating and presenting the charge system, then the reservoir system, the trap and seal, and then we'll conclude with a discussion of showing them how they can make money with your prospect. The first step in your presentation is to set the stage for management or the judges. Where in the world is your prospect? Is there a working petroleum system? And is there production or discoveries nearby? Since management may see prospects from all over the globe, when you present to them, you need to set the stage by orienting them. So they need to know where in the world your prospect is, or at least where in your company's portfolio your prospect is situated. Management need to know where the basin is located, as well as the regional setting. Start from a high-level perspective and then drill down. For this presentation, we will use the Nam Can Sam Basin. It is located offshore Vietnam in the South China Sea. It's one of several late Eocene to Oligocene age rift basins in the region, several of which have established prolific hydrocarbon production. If your prospect or your project area is offshore, management will also need to know the water depth that encompasses your project area. Since management often see prospects or projects in multiple areas, it often helps to give them a relative scale for your project area. In this case, we've overlain the state of Louisiana across the Coulong and Nam Can Sam basins to give them an idea of the scope of your prospective area. As you drill down to a more local setting, management are going to need to know the structural architecture of the basin in which your prospect is situated. Where are the highs and lows, and how deep are the lows? This is best done with a basement map or a map of a horizon that defines the base of the petroleum system. Likewise, they need to know the stratigraphic architecture of the basin and whether or not the basin has source rocks, reservoirs, and seals. This is usually best done with a chronostratigraphic chart or a Wheeler diagram, but can also be done with regional cross-sections. To help management better understand the potential risk and reward of your prospect, they need to know how well the basin's petroleum system is working. How many wells have been drilled in the basin, and what percentage of those basin wells are dry holes? Of the wells that encountered hydrocarbons, how many were non-commercial discoveries or technical successes versus how many were commercial discoveries? Did the wells encounter oil or gas, or both. Time and data allowing, each dry hole should be explained. However, you'll often not have the time or at least the information you need to assess why certain wells failed. In our example of the non-con sound basin, it's generally considered to be a gas-prone basin because of the nature and burial depth of the source rocks. Yet for a portion of the non-con sound basin, as seen in this map, we can see that many of the fields have encountered at least some oil. Finally, if possible, you need to provide management with an assessment of the amount of reserve additions per year that have been achieved in your prospect area, as well as the field size distribution for your area. Scout services often have this information, but at a cost. Some public domain information and publications may be found on the internet, and for some basins that information is free. And for other basins or areas, it's available but for purchase. You may not be able to do this in the IBA competition, but you should always try to do this when you're working for a company and presenting to management or investors. Looking at the reserve additions per year can give you a good idea of how mature a basin is. Companies tend to drill the larger and easier to identify prospects first, such that over time, the amount of reserve additions diminish, at least until someone drills or tests a new play concept. Looking at the field size distribution gives you a benchmark for your prospect. In the non-con Som basin, the average commercial field is about 60 million barrels of oil equivalent. If your prospect is 120 million barrels, you are double the average and well into the tail of the distribution. That may be possible, but it's not likely. Now that you've set the stage for management, it's time to show them the elements of the petroleum system. Those elements are the source rock, the migration pathway, the reservoir, both presence and quality, the trap, and the seal. Since source rock and migration are the foundational elements of the petroleum system, we'll start our presentation with those. Source rocks are rocks that are rich in organic matter, which, if heated sufficiently, will generate oil or gas. Typical source rocks, usually shales or limestones, contain about 1% organic matter and at least 0.5% of total organic carbon, although a rich source rock may have as much as 10% organic matter. There are three types of source rocks, type 1, 2, and 3. The classification is based on the content of hydrogen, carbon, and oxygen, and are typically shown in a Van Creveld diagram. Type 1 source rocks have mainly algal and saprogenic kerogens and are often associated with anoxic environments such as lake sediments. Type 2 has lipid-rich kerogen, generally from planktonic origin, and are mainly associated with marine sediments. Type 3 has humic kerogen derived from plant material. Most coals are type 3 source rocks. Type 1 and type 2 source rocks generally generate oil, while type 3 is mainly gas, but not always. In the non-con Som basin, for example, the principal source rocks are type 3 coal sequences, but they do generate some liquids. 1. Algal source rocks are most common in lacustrine settings, such as rift basins, but they're also common in subca environments. Lacustrine source rocks are often finely layered due to seasonal variations in the lake temperature. They consist of alternating beds of organic-rich and non-organic mudstones. Algal-rich source rocks deposited in subca environments also tend to be layered, consisting of alternating beds of organic-rich mudstone and evaporites or carbonates. Type 2 source rocks are generally formed by marine plankton. Planktonic activity is usually highest where oceanic currents can carry materials to high-latitude coastal areas, or where upwelling carries nutrient-rich material from deep water into the photic zone. Type 3 source rocks are associated with coals and coaly deposits. They typically form in peat swamp forests or in coastal mangrove swamps in broad tidal areas. More localized coals can be deposited in the interfluvial areas of anastomosing rivers or abandoned river channel. Looking at the non-Consan basin, we can see that the Tien Cow Formation consists of alga-rich lacustrine source rocks deposited in the rift lakes. The overlying Cow and lower Dua formations contain abundant coals deposited in a swamp environment. There are only a handful of Tien Cow penetrations in the non-Consan basin, mostly in the southwest. These wells encountered coarse-grained fluvial deposits, with only one well encountering thin coals. However, looking at the depositional environment in the lower Oligocene, lakes are interpreted to have formed in the deeper portions of the rift basins. These served as the locus for alga-rich lacustrine shales developing in the deeper portions of the lakes, and thin coaly shales in the shallower portions of the rift basins. By upper Oligocene, marine incursion of the basin resulted in the development of a massive brackish water swamp and the deposition of mangrove coals. Once the source rocks have been deposited and preserved, they must be buried and cooked. You'll need to determine the thermal gradient for the basin or the portion of the basin for which your prospect is located in order to determine when that expulsion will occur. In general, at 30 degrees centigrade, organic matter begins to change into kerogen, a solid form of hydrocarbon. When the source rock is heated to approximately 60 degrees C, the kerogen begins to change into oil. Maximum expulsion of oil occurs at around 130 degrees C. At 150 degrees C, the source rocks begin to generate dry gas, and at 225 degrees C, the source rock becomes over-mature. Depending on the nature and richness of the source rock and the rate of burial for your basin, these temperatures will vary. So ideally, you need to determine the depth and temperatures at which the source rocks in your basin become thermally mature by using tools such as vitrinite reflectance or the thermal alteration index. Once you know the thermal gradient for your basin and the temperatures at which the source rocks in your basin become mature, you can model the basin's hydrocarbon generation. You can do this with modeling software, or you can do it by posting the oil and gas windows on a cross-section. Looking at the thermal gradient for the non-Consan basin, we can see that at present day, the source-prone Tien Cow, Cow, and lower Dua formations are over-mature, that is, they're below the gas window, except on the flanks of the basement horst block along the northwest margin of the basin. If we palinspastically reconstruct the cross-section to the Cow Formation, which is 23 million years ago, we can see that the Tien Cow Formation is in the oil window, transitioning to the gas window in the deeper parts of the basin. The coals of the Cow Formation have yet to enter the oil window. Once we know where the source rocks were deposited and when they begin to expel oil and gas, we need to look at the migration pathway. The migration pathway is the route that the hydrocarbons will follow to get from the source rock where they are generated to the reservoir in which they are stored. Certain seismic attributes, such as similarity, can highlight hydrocarbon migration pathways. Likewise, mapping faults that extend from the source rocks to the reservoir section can show how migration fairways can connect the reservoir and the source rock. This map of the non-Consan basin shows the present-day thermal maturity of the basin, and we can see most of the basin is presently over-mature. The migration vectors are shown to illustrate where hydrocarbons would migrate once they're generated. The migration vectors will point from the lows to the highs and will be oriented perpendicular to the structure or the isopac contours of the basin. We can also illustrate this using a common risk segment map. Common risk segment maps use a traffic light system to illustrate relative risk. Red indicates where a petroleum system element, in this case charge and migration, is considered high risk, and that area should be explored with caution. Yellow indicates where the petroleum system element is considered somewhat risky, and due diligence should be applied to all elements of the prospects in that area. Green indicates where a petroleum system element is considered low risk, and that area should be explored aggressively. Once we've documented the charge and migration system, we need to define the reservoir presence and the reservoir quality. The reservoir is the container in which hydrocarbons are stored. There must be sufficient porosity to hold the hydrocarbons and sufficient permeability to allow the hydrocarbons to flow from the reservoir to the wellbore. And looking at conventional reservoirs, we're either looking at sandstones or limestone. However, any lithology may hold hydrocarbons. Unconventional reservoirs are typically formed by fractured granites or volcanics or by fractured carbonates. With advances in hydraulic fracturing technology, height sandstones and even source rocks can now be considered reservoir. In the Nankan San Basin, the Dai Hong horse produces from the fractured granites. The first step in predicting the reservoir you expect to encounter in your prospect is to use the nearby well control and construct cross sections, or to use seismic stratigraphy, or ideally both, to determine the depositional setting and the reservoir distribution. This size-form section across the Nankan San Basin combines sequence stratigraphy with the well control, although we can't show that for proprietary reasons. This shows us the distribution of the reservoirs in the Nankan San Basin. When making subsurface interpretations, we are always data limited. The art to making a good interpretation is to understand the depositional patterns. To do that, we have to know the processes that control the depositional patterns. There are two sedimentary processes that are of interest to understanding and predicting reservoir distribution and reservoir connectivity: the processes associated with sediment delivery and the sediment dispersal, and the processes associated with the interplay between sediment input and the creation of accommodation space. Our ability to predict reservoir presence or map net reservoir in clastic depositional systems is dependent on our understanding of the depositional geometries of the various depositional systems and the various patterns within those systems. The process associated with sediment delivery and sediment dispersal is the fundamental control on the architectural geometry of the depositional system. The process associated with the interplay between sediment input and accommodation space are the fundamental control on the lateral and vertical stacking patterns within the depositional system. Plastic depositional systems exhibit one of two principal stacking patterns: finding upwards patterns associated with delivery systems and coarsening up patterns associated with dispersal systems. Depositional systems associated with the delivery of sediments from the provenance to the basin exhibit a linear geometry. That is, the system is many more times longer than it is wide. Within the linear geometry, there can be considerable variation in the depositional patterns, and there are four depositional patterns: braided rivers, meandering rivers, anastomosing rivers, and incised valleys. Depositional systems associated with the dispersal sediments in the basin exhibit a lobate to fan-shaped geometry. That is, they are narrow at the head of the system and wide at the base. There are three dispersal systems: alluvial fans, deltas, and submarine fans. The geometry of each of these systems and the patterns within those geometries are similar for each depositional system, regardless of whether that depositional setting is subaerial or subaqueous. For example, dispersal systems are all lobate in geometry, whether they are deposited in the base of a mountain or at the base of slope in deep water. Likewise, the four patterns that we see in delivery systems are the same, whether they're deposited in a subaerial environment or in a subaqueous environment. Likewise, the geometries and the patterns of facies within those geometries for each of the depositional systems are also fractal. That is, the pattern is the same at all scales, from several centimeters to several hundred kilometers. Note the similarity of the depositional pattern of the two braided rivers. The upper example is the Brahmaputra River, one of the largest rivers in the world. The lower figure is a small rivulet only a few centimeters wide. Likewise, the delta pictured in the upper right is the Mississippi River Delta. The delta shown below is a crevasse splay from one of the distributaries of that delta. In that the geometry of the depositional systems are similar, regardless of the depositional setting or the scale, the patterns within the geometries are also similar and therefore predictable. This is a powerful concept that the interpreter can use in predicting the depositional geometries and the reservoir patterns. Whether the reservoir should be hundreds of kilometers in scale or a kilometer, the geometry of the deposit is similar. Therefore, interpreters need only become familiar with the basic geometries of clastic depositional systems and the patterns of the facies that occur within those geometries. Looking at delivery systems, there are four patterns: braided rivers, meandering rivers, anastomosing rivers, and incised valleys. In the dispersal systems, there are three settings: deltas, alluvial fans, and submarine fans. For conventional plays, reservoir quality is just as critical as reservoir presence. Porosity tends to decrease with depth, so unless there is some method to preserve porosity at depth, such as early hydrocarbon migration, or some diagenetic event to enhance porosity, there is generally a limit to how deep we can explore and expect to encounter reservoirs with sufficient quality to be productive. Aeolian systems also deposit clastic reservoirs. Aeolian deposits are windborne systems that can form anywhere there is a source of dry sand and wind. As such, it's a hybrid delivery and dispersal system. The wind disperses the sand away from the source, but also delivers it to the site of deposition. Aeolian systems require a large quantity of dry sand and sufficient wind velocity to move that sand. Once an aeolian system has been identified, either through well control or seismic, exploration is relatively easy for reservoir as the sands are ubiquitous across the dune fields. The challenge in exploring for aeolian systems is ensuring that the source rocks and seals are present and preserved. The conditions are commonly found with aeolian deposits in subenvironments and in subaerial interior basins in which the basin floor is below sea level, such as Australia's Lake Eyre. We'll now look at carbonate reservoirs. The key difference between carbonates and clastics is that clastic sediments are transported often over large distances. Carbonates grow in place or are transported very short distances from where they grow. Carbonate deposition is controlled by both climate and water depth. The majority of carbonate production occurs between 1 and 10 meters of water depth. In water depths shallower than 1 meter, wave action tends to kill carbonate generating organisms. In water depths greater than 10 meters, light conditions begin to get too dark for many organisms. There are two principal carbonate depositional systems: carbonate ramps and carbonate platforms. Carbonate ramps form where reef constructing organisms are absent or where conditions inhibit their development. Carbonate ramps are typically divided into three areas: the inner ramp, the middle ramp, and the outer ramp. Carbonate platforms develop where reef constructing organisms are abundant. Carbonate platforms are subdivided into the tidal flat, the shelf, and the shelf margin. The tidal flat depositional sitting on carbonate ramps and carbonate and platforms is similar. In carbonate reservoirs, the depositional fabric and the diagenetic processes are just as important or even more important than burial depth in controlling porosity and permeability. There are four principal reservoir facies in the non-Somme basin: fluvial and lacustrine deltaic sediments associated with the rift section, and tidal bars, carbonates, and turbidites associated with the marine post-rift section. The deeper Tian Khao and Khao reservoirs, however, except along the basin margins, are generally too deep to have sufficient reservoir quality to be viable targets. As such, the principal reservoir targets for the non-Somme basin are the tidal bars, carbonates, and turbidite facies of the post-rift section. Depositional environment maps, shown here, can help management understand both the nature of the depositional system and the distribution of reservoir systems. By early Miocene, the Nankan San Basin had been flooded by marine waters. The basin was now a narrow seaway with extensive tidal bars being deposited. Coastal mangrove swamps were now locally situated along the coastal margins. The basin continued to open up such that by Middle Miocene, it was no longer a restricted seaway. Along the northern margin of the basin, tidal influences gave way to wave and longshore drift, and carbonate development occurred on the basement highs. As with the source rock presence and migration, we can use common risk segment maps to show management where in the basin we can expect to find reservoir of suitable quality. Those areas shown in green are the areas where we expect reservoir presence and quality to be low risk. Next, we need to define the trap and the seal. The trap is a geologic structure or a stratigraphic feature capable of retaining hydrocarbons. Hydrocarbon traps that result from changes in rock type or in pinch-outs or unconformities or other sedimentary features, such as reefs or buildups, are stratigraphic traps. Hydrocarbon traps that are formed in geologic structures, such as folds and faults, are structural traps. Any mixture of the two results in what we call a combination trap. The most common anticlinal traps in extensional basins are rollover anticlines. In extensional settings, the fault bend fold, the fault propagation fold, and the detachment buckle are more common. In strike slip settings, we can see en-echelon folds or flower structure anticlines. For basins which have undergone extension followed by compression, we'll see inversion structures. Once we've determined the type of structure that comprises your prospect, you must ensure that you understand the general geometry of that type of structure and that your structure maps reflect that geometry. Although many anticlinal closures are compartmentalized by faults, for this discussion, we will constrain our definition of fault traps to be traps formed solely by the presence of a fault. There are 4 types of fault traps. In extensional settings, we have upthrown and downthrown fault closures, and in compressional settings, we have hanging wall and footwall closures. Fault traps, whether extensional or compressional, have an inherently higher risk for seal than do anticlinal closures. The key to exploring for fault closures is to find those fault closures that can constrain regional migration. Looking at this line from Mozambique, we can see that the regional migration direction is from east or the right, or to the west or left. The red arrows show those potential fault closures that are not oriented in such a way as to stop regional migration. They have a higher seal risk. The green arrows are those fault closures that can potentially trap regional migration and have a lower seal risk. We'll now look at unconformity traps. One of the more common types of unconformity traps are sub-unconformity truncations. With sub-unconformity truncations, there's an unconformity wedge defined by where the top of the reservoir is truncated by the unconformity and where the base of the reservoir is truncated. Therefore, it is important to map the top and the base of a reservoir in a truncation trap. You also need to be aware that the sand thickness that you observe below the unconformity may not be the complete sand, but a partially eroded remnant of that sand. We can also have supra-unconformity traps. These consist of reservoirs that are onlapping an unconformity, such as that seen in this cross-section offshore Borneo. Or we may have both sub-unconformity truncations and supra-unconformity onlap traps, such as we see in this cross-section in the northwest margin of the Yungar Basin, northwest China. Over the course of my career, I reviewed or audited hundreds of maps. And unfortunately, most of those maps are, at least to some extent, wrong. And almost any map coming out of the workstation will be incorrect to some degree. Many maps are not only geologically improbable, but geometrically impossible. So once you've generated your map, it's important to conduct a self-audit to ensure that the interpretation and map is valid. To do that, you want to conduct a self-audit, which consists of 6 steps. Does the map honor the data? Do the contours exhibit contour compatibility across the faults? Do the contours honor vertical separation across the faults? And are the fault traces correctly located? Then make sure that the map matches the seismic and the map honors the geology. To see how to apply such an audit, you can go to SCA's website and review the webinar, Would You Approve Drilling a Dry Hole? Once you have a valid structure map across the trap, you're ready to evaluate the final element of the petroleum system, the seal. The seal consists of a rock or horizon with low permeability or higher lithostatic pressure than the reservoir, such that the hydrocarbons cannot migrate into it from the reservoir. We must evaluate 2 types of seal. Lateral seal, which prevents hydrocarbons from moving laterally out of the potential trap, and vertical seal, which prevents hydrocarbons from flowing up out of the reservoir. If the hydraulic pressure of an oil or gas column exceeds the fracture gradient of the overlying seal, the seal will fracture, and the hydrocarbons will migrate out until the hydraulic pressure is reduced below the fracture gradient. Overpressure occurs when formation fluids are unable to escape. If the overpressure becomes too great, it will reach the fracture gradient and begin to fracture both the reservoir and the seal. A fracture gradient is the pressure required to cause fractures in a rock at a given depth. Plotting the actual subsurface pressure from RFT data, leak-off tests, drilling mud weights, or from seismic velocity data, along with plotting the hydrostatic and lithostatic gradients versus depth, will show you how close the subsurface conditions are to reaching or exceeding the fracture gradient. The hydraulic gradient for fresh water is 0.43 psi per foot. The gradient for saturated salt water is 0.46 psi per foot. For more information on making a pore pressure plot, see Crane's Petrophysical Handbook. When permeable rocks are juxtaposed across rocks with greater or equal permeability or lower lithostatic pressure, then the hydrocarbons can continue to migrate across the fault. One way to assess seal is to calculate the shale smear factor, or SSF. As the fault moves, shale will tend to smear into the fault zone. The shale smear factor is determined by dividing the fault offset by the thickness of the shale bed. The lower the shale smear factor, the more likely it is the fault will seal. A similar method for evaluating seal is to determine the shale gouge ratio. To determine the shale gouge ratio, take the total thickness or the total net shale and divide it by the fault offset. Several studies have shown that for traps with a shale gouge ratio of 0.2 or less, the traps never contained hydrocarbons. When the shale gouge ratio was 0.3, a few traps would work, but most did not. With shale gouge ratios of 4 or higher, the traps started to work. The shale gouge ratio is the inverse of the net to gross sand ratio. As such, a highly effective method for evaluating both reservoir potential and seal risk is to construct a net to gross sand map, or a sand percent map, of the target reservoir and overlay it with the depth or time structure map of the prospective horizon. Here we see a simple structure map for a downthrown three-way fault closure. Note that the dip of the upthrown side of the fault is away from the structure, so if the fault does not seal, hydrocarbons will migrate away from the trap. Here's the net to gross or sand percent map, color-coded by facies. The depositional environment is a barrier island and tidal delta. We now overlay the 2 maps. Where we see high sand percent values intersecting the fault, we color code the fault red. Where we see sand values intersecting the fault with low sand values, we color the fault green. Orange is used to indicate where moderate sand percent values intersect the fault. The advantage to this method is that we can now see where the reservoir is expected to be best developed in the trap, as well as where the trap is likely to fail. The final seal risk map for this prospect illustrates that we can expect the seal risk for this trap to be quite high. Once we combine the reservoir and the fault seal risk, we can use that information to determine the P10 and P90 trap areas, as well as determining our seal risk. For faults in the downthrown horizon, if they're juxtaposed against different horizons in the upthrown block, we need to make a net to gross sand map for each of the two horizons, upthrown and downthrown. Now that we've evaluated the petroleum system, the trap, and the seal, we have to show management that this prospect has the potential to be profitable. To do that, we have to look at both uncertainty and risk. To have the best chance possible of making money, management needs to know, as accurately as the data allows, the full range of uncertainty for each element of the petroleum system and the risk or chance of occurrence for each of those elements to be working in the petroleum system. Many interpreters, and managers for that matter, assume that uncertainty is the same as risk. It is not. The two are very different. Uncertainty is the range of possible outcomes. Looking at this sonogram, the possible outcomes are girl or boy. And if we have multiple births, we can have twins, triplets, quadruplets, or so on. Risk is the likelihood of realizing that specific outcome. So for girl or boy, it's 50-50. The likelihood of achieving twins is 0.02. For triplets, it's 0.0001. And for quadruplets, it's 0.00001. With the exception of the constant that converts square feet to acres, all the elements of a volumetric calculation, in this case, original gas in place, has uncertainty associated with it. So we have to determine the amount of uncertainty we have in the area, the net pay, the porosity, the saturation, and with gas, we also have to look at the percent non-combustible gas, as well as the formation volume factor, which converts the volume from subsurface conditions to surface conditions. The less information we have about our prospect, the higher the uncertainty range will be. As we accumulate more and more information, the amount of uncertainty will reduce, but will never go away. Since all of the factors in the volumetric calculation, except the constant, will plot on a semi-log paper as a straight line, or very nearly plot as a straight line, we can use the probability plot to define the distribution. And since the points plot as a straight line, we only need 2 points to define the distribution, usually the P10 and P90. In this particular example, the parameter we're plotting has a P90 value of 200 and a P10 value of 1200. We connect those 2 points with a straight line and end up defining the entire uncertainty range for that parameter. When mapping structural closure area, we usually can define the spill point or the maximum closure area. When we can do that, it's generally better to post the P1 value, which is the largest the prospect can be, and then go halfway up from the P1 closure area to the crest of the structure, which will define the P50 closure area. These numbers are more objective than they are subjective. The use of probability theory to define our uncertainty was championed by Pete Rose. And he showed that we can define the full range of uncertainty with a probability plot. His philosophy was such that we can use the P1 and P99 values on the distribution to provide reality checks to the full distribution. He states that the P99 value we can get on our plot must be realistic and measurable, and the P1 should be possible, but large enough to make us somewhat uncomfortable. This is an example of a porosity plot. We posted the P90 value as 6% porosity and the P10 value of 25% porosity. And when we look at the full distribution, however, we see that the P1 value for porosity is 45%. That's not possible in a clastic reservoir, as depositional porosity tends to be less than 40%. So looking at this distribution, we recognize that we need to adjust our inputs to reduce the P1 volume to something that is realistic. When evaluating prospects and looking at portfolios, we have learned that if we can eliminate or at least reduce systematic bias, and if a company drills enough wells, you're likely to find and produce the pre-drill risk mean. We use the Swanson's mean, which is calculated by taking 0.3 of the P90 value, adding 0.4 of the P50 value, and then again adding 0.3 of the P10 value. The Swanson's mean will plot on your probability distribution pretty close to the 40% line. So as mentioned, we need to define the uncertainty range for each element of the petroleum system. For the source rock, how much source rock do we have? How good is it? And will it generate oil or gas or both? Looking at the migration pathway, we have to define where the hydrocarbons will go once they're generated and determine when they got there. For the reservoir, we have to determine how many pays we're likely to have and how good and the quality of reservoir they are. For the trap, how big is it and where's the spill point? And for the seal, how much column can we expect that prospect to hold? Once we've defined the uncertainty range for each of the variables of the petroleum system, we then assign a probability to those variables. And again, probability is the likelihood of any outcome. So we have to define the probability of having that source rock. In other words, what's the chance that the source rock is present and mature? What's the probability that we have a migration pathway connecting the source and the reservoir? What's the probability that we have both a reservoir and a reservoir of sufficient quality? What's the probability that we've mapped the trap correctly? And what's the probability that if we have that trap, it will seal? In practice, assessing the chance of success for any prospect is highly subjective. We have to look at source, migration, reservoir, trap, and seal. What we see through experience is that most interpreters have an understanding of what they think the overall chance of success will be. In this case, about just below 25%. But when different interpreters look at the prospect, they achieve that overall chance of success by different pathways. The first interpreter, shown in orange, assumed that the trap risk was going to be the highest risk. The second interpreter, shown in blue, assumed reservoir was going to be the highest risk. And the third interpreter looked at trap and seal as nearly equally high risk. Industry has looked at a number of means to try to reduce or eliminate that subjectivity in assessing chance of success. This is an example of one of those schemes. It's a chance adequacy matrix. And it assumes that if we have no information, we'll assume that the chance of success is 50-50. If we have bad news, we'll make the chance of success for that element less than 50-50. And if we have good news, we'll make it more than 50-50. It turns out that most of the schemes that have been developed to eliminate subjective bias in assessing risk are just as subjective as the traditional method. One method that does show promise for eliminating or at least reducing bias in chance of success assessments is the Delphi method. In the Delphi method, each interpreter or a group of interpreters will write down privately their assessment of the risk and each element of the risk. Once they have that done, they'll discuss each element of the risk as a team and then once again calculate the chance of success using the input from the team. So in this case, after our three interpreters discussed the risk of the prospect and why they thought each risk was pertinent, they reassessed the risk. And what we can see is that after the discussion, all of the interpreters settled on trap as the critical risk for the prospect. The overall chance of success did not change, but the path that they took to get there did. This allows management to identify the key risk, in this case trap, and make a decision as to whether or not they want to invest additional funds to mitigate that risk. Once we've assessed the uncertainty range and the chance of success, we can estimate the risk mean by multiplying the mean volume from our distribution times the chance of success. If we have a prospect consisting of a single reservoir target, The chance of success will represent the chance of entering the hydrocarbon distribution or failing. If we have multiple targets, we have to determine the uncertainty range and chance of success for each of the targets. We can then sum the mean, or we can aggregate the volumes for the P10 and P90. This concludes the presentation on evaluating and presenting prospects. Again, I would encourage you to go to Subsurface and Consultants and Associates website, and under the Resources tab, you'll find a number of on-demand and free webinars available. Many of those could help you in developing your prospect or your presentation to the judges. What we presented in this presentation will hopefully help you with the IBA competition, but should also help you throughout your career. So on behalf of the IBA committee, the American Association of Petroleum Geologists, the Division of Professional Affairs, as well as SCA, we'd like to wish all of you the best of luck in your competition. Thank you.